Welcome to the series of videos on topology. Now previously we have seen the definition of closure of a set, interior of a set. Now today let us see what is the definition of or what is the meaning of limit points of a set, and then we'll make a short videos. So first we will define what are the limit points of set, then we will take one two example, then we will find the set of all the limit points of closed interval or open interval 0 1 in R with usual topology. Another example we will take in the next video. So altogether we will divide this topic into 3-4 parts in short videos. Okay. So let us first define what is a limit point of a set. Limit point of a set. Okay. This is also called as cluster point, or it is also called as accumulation point. Different nomenclatures are there. So let us define this first. Let X be a topological space. Let X be a topological space, and let us take a subset of X, and A be a subset of X. And now we have to check what is the limit point. So we will take a point in X. Let X belongs to X. Okay, so we have a subset of X, and we are checking whether this X, a point from the whole space, is a limit point or not. So let X belongs to X. We say that X, small x, is a limit point of A if, let me change the color, if every neighborhood of X contains a point of A other than X. Understand? So this X is a limit point of a set A. If you take any neighborhood of X, it will intersect with A at a point other than X. That's how we define the limit point. Now if you want to put this in a notation like that is, if you take any neighborhood U of X, if you take the intersection of it with A and then you remove the point x0, X, right, and this should contain a point, that means this has a point of A, this has a point of A other than X, so this has to be non-empty. Okay, that is also we can say you take a neighborhood and then you remove a point from A, then you take the intersection of it, this will be non-empty. It's one and the same. Also we can say that you take U, you take out the element, that X from U, you take the intersection with A, this should be non-empty, and this should hold for every neighborhood, right, for all neighborhoods U of X. Okay, this should hold for all the neighborhoods U of X. Okay, there's a nomenclature. We will say if, okay, this is the definition of the limit point of a set. Okay, so we will modify it. If U is a neighborhood of X, then U difference this X. So you take a neighborhood and you remove that point from that X from U, same point. Then when you remove this, this is called a deleted neighborhood of x. Okay, and with this we can put up this definition in the following way. Let me put a star. X is limit point of a, limit point of a if every deleted neighborhood of x contains the points of a, that is intersects a. You understand? Let me go back. So this small x, it need not be in the given set. It may be outside the set. Okay, we are taking a small x from the whole space x. Then this x is called the neighborhood of is called the limit point if you take any neighborhood of x that should contain a point of a other than x. Okay, or in other way we can say x is the limit point of a if every deleted neighborhood of x intersects a. That's how we define the limit point of a. Okay, then again we have a nomenclature, some definition. If you take, let me write it as a note. The set of all limit points of a, limit points of a in x is called the derived set, derived I, derived, derived set, and is denoted by, you write derived set of a and then you write where you are taking the derived set, where you are finding the limit points, and this you are finding in x, so derived set of a in x. If you remember, we have used the nomenclature, the closure of a in x, right? We are finding the closure of a in x. We have written int a x. This is interior of a in x. If you are not watched those videos, please go to the playlist and clear out your doubts from those videos. Okay, so set of all the limit points of a set A is called a derived set of A, and it is denoted by d a, and you write the suffix x. X is the topological space. Okay, let us take two examples in this video, and the next video we will take another example. So example, let us take our topological space to be R. We might have already done this in the matrix spaces with our usual topology we'll take, and let us take a subset Q of R. And question is, what is derived set of Q in R with usual topology? That means you have to find the set of all the limit points of a set Q. So if you have this R and there is a Q, so you know that Q is countable, and complement of Q, that is set of all the irrational numbers, are uncountable. So there are uncountably many irrational numbers, there are countably many rational numbers, and you also know that R is uncountable set. Okay, now let us check what are the limit points of Q. So let us take, say, alpha. Let this alpha belongs to R, and we have to check whether this alpha is the limit point of Q or not. Okay, we will take this alpha arbitrarily, and to check that we have to see that if you find a neighborhood of any arbitrary neighborhood of alpha, that should contain a point of rational other than this alpha. Okay, this alpha can be rational, it may be irrational, that we are not bothered about. Right, so let alpha belongs to R, and let U be neighborhood of alpha. Now you know that U is neighborhood of alpha, U is neighborhood of alpha, and alpha that means alpha belongs to U and U is open. So if U is open, this implies there exists some R greater than 0 such that the basic neighborhood, that is alpha minus R, alpha plus R, contained inside U. That is by the definition of open set. Neighborhood means it's open set. Okay. Now this implies there are two real numbers. It may be rational, it may be irrational, but we have two real numbers, alpha minus R and alpha plus R. And we know that from the course of real analysis that between two real numbers there always exists a rational number. So this implies there exists some rational number, say P, belonging to a rational number Q, such that this alpha minus R less than this P and less than this alpha plus R. Now here we are assuming the result, or we are accepting the result, that between any two real numbers there exists a rational number. In fact, you can prove that fact. Okay, try to prove that fact. So there exists a rational number such that alpha minus R is less than P less than alpha plus R. That means this P belongs to this open interval, and this implies if you take the open interval alpha minus R and alpha plus R, and you take the intersection of this with Q, this will be non-empty, as P is in both sets, right? And since this P need not be same as alpha, because here you are taking alpha minus R is positive, alpha plus R, which is R is positive, right? That means this P is not equals to alpha. So even if you remove this alpha from this set, still it will be empty, non-empty. That implies alpha minus R, alpha plus R, intersection with Q, you remove even if that alpha, still it is non-empty. This implies, let me go in the next page. This implies alpha is limit point of Q. And what is alpha? We have taken this alpha from a real number which is arbitrary. We have not put any condition on that alpha. And if you take any real number, you can do this and you can show that that is a limit point of that set of rational numbers. That implies, therefore, every point in real number is limit point of rational number. Hence, derived set of rational number in real numbers is nothing but set of all the real numbers. Okay, in coming videos we'll talk about the dense set. So here we can say that Q is dense in R. The definition we will see as we proceed. Okay, another example which is very very simple. Let us change our topology. Let us take lower limit topology. So example. So for this, let us take lower limit topology. So consider, if you remember, we write lower limit topology to be R suffix L. Okay, RL. Let me put it for you. R with lower limit topology. Take RL, that is R with lower limit topology. And for this, we know that the basis. So what is the basis for lower limit topology? This is set of all the intervals of the form open, close A, open B. That is, from left hand side it is closed, and from right hand side it is open, such that this A comma B belongs to R, and A is less than B is the basis, right? and this basis generates topology that is nothing but the lower limit topology, okay, that we have seen in the previous videos. Now with this, the question is, what are limit points of, say, open interval 0 1 in R with lower limit topology? You pause the video and try to find the answer for this. Try to get the derived set of the open interval 0 1. But again, remember here, what are your basic open sets? Neighborhoods. And based on that, you apply your definition of the limit point and try to get all those limit points, and that set which contains all the limit point is called the derived set of the given set. Okay, so let us draw a diagram first here. Let us try to understand and then we will write. We have this real line R, and then we have 0 here, say 1 here, and we have open interval 0 and side also 1. Okay, now we have to find what are the limit points of this set 0 1. But again, remember the point when we define our limit point, we have taken a point x from the whole set. So we have to check what are the limit points of this set. That means we have to take the points from whole of R. Okay, now for example, if you take a point here, let us take one point, let us take point here, some point here, right? So the definition says if you take any neighborhood of that point and if you intersect with the given set, it has to be non-empty, and then non-empty even if you remove that point. Okay, so my claim is the point which is greater than 1 cannot be in the derived set of A. Okay, why? So let us take different cases. We take different cases. Okay, first case 1, let us take a point this side less than 0. So x belongs to minus infinity comma 0. We will not include 0. Okay, then we will take further cases, and if you want you can plot the two cases together. Okay, it's up to you. Alright, now x belongs to minus infinity comma 0 1. Now for this, is this a limit point? That you have to check. Now you have to find the neighborhood of this point. When you take the intersection with this, it should be non-empty. Okay, that is, let me write here, that is minus infinity less than x less than 0. We are checking whether this point x is the limit point of this set or not. Okay, now we have to check whether this is a limit point. That means for every neighborhood, that deleted neighborhood should intersect the given set. Alright, now my claim is this is not a limit point. So I'm already saying that this is not a limit point means you have to get, or that means there exists a neighborhood of this x. When you take the intersection with this set, it is empty, and hence x is not a limit point. Okay, so let me write that x belongs to this. Let us take the neighborhood. Take this x, whatever x you have, you take this x here, and let us take 0 open. Okay, so for any point x, now if you take this, then this is neighborhood of x, because this is how you define this. A is included, right? This is closed, so even in this x is included, so this is a neighborhood of x. Okay, these are the open sets in lower limit topology, basic open set, but this is not open in are with usual topology or standard topology. Okay, so first, that's why we have written derived set in x, that suffix x. Okay, so now let us take this is a neighborhood of x, and if you see, this is negative this side up to 0. This is not includes, this does not contain 0. This implies this x comma 0 intersection with open interval 0 1 is empty, not empty, is empty, because here you are coming up to 0, here we are starting from 0, and in both the sides 0 is not there, so the intersection is empty. Hence this implies, therefore x is not the limit point of open interval 0 1. So any point less than 0 is not the limit point. Okay, let us check the same thing for any point which is greater than 1. Case 2, let x, or let me write x belongs to open interval 1 comma infinity. That means this x is greater than 1. That is 1 less than x less than infinity. And now again you have to check whether this is the limit point. So you guess this, whether it will be a limit point. Of course this is not a limit point, because no matter where your x is there, we can take a neighborhood. So for that, let or here let us find our neighborhood. Here we will take a neighborhood as x comma say x plus 1. Okay, if you take this, of course this x belongs to this and x is greater than 1. Okay, this is neighborhood of x, and when you take the intersection of this x comma x plus 1 with open interval 0 1, this will be empty again, because here x is greater than 1. Even if you include x is equals to 1, still here you will have your interval will start from 1, and here the 1 is not there, so still there is no problem. So again we can just modify this and we can write x belongs to close interval 1 to infinity, that is 1 less than equals to x less than infinity. So even if you take x equals to 1, still this is empty, and hence x is not the limit point. Understand this? Okay, so we are exhausted. We have taken all those points up to 0. We have not included 0. We have started from 1 and all those points towards the right. Those are not the limit points. The remaining points now are 0 included and 1 not included. So we have to check the points in between this now. Okay, let us check case 3. Case 3, let us take x belonging to 0 1. 1 is open. So let us check whether this is the limit point of this or not. Okay, that is 0 less than or equals to x less than 1. Okay, now let us take that u be any neighborhood of x. Let us take any neighborhood of x. Let me again draw the diagram for you. This you have, this is 0, this is 1. So in this case we have included 0 and excluded 1, and now that x can be anywhere in this interval. Okay, x can be here. Now our claim is this x is a limit point. If you take any point in this closed interval 0 open interval 1, then it's the limit point. That's what you have to prove. Okay, now here to prove this we have taken any neighborhood of x. Since it's a neighborhood that is open, there exists a basic neighborhood that contains inside U. Okay, so let us take that. This implies since U is open, there exists a basic neighborhood, that is, or how are the basic neighborhoods? That is, there exists r greater than 0 such that the basic neighborhood, say x comma x plus r, contain inside U. Okay, U is open and x belongs to U, and by the definition of the open set, there exists a open basic neighborhood such that x belongs to that neighborhood and that contains inside U, and that's what we have used here. Okay, now this is x. Alright, let me change the color. This is x. R can be anything. If r is less than 1, if r is somewhere here, then you are done, you are taking this. Okay, but if we don't know what is r, right, and again we don't know what is U, so U can be something like this, U can be something like this, it can be outside the given set, and then this r can be over here. So as it is, this cannot be, or this cannot be inside 0 1. Okay, but if you know that, but if you find some r which will guarantee that that is less than this, then you are done. Okay, and for that let us take delta to be minimum of 1 and x plus r. Okay, x plus r can be here, right? You take the minimum of 1 and x plus r, and then you take the open interval, and then you are done. This implies to take this x comma x plus delta, or let us take delta by 2, half of it, take the open interval, that will be inside U. Okay, because if you are taking the minimum of it, so if 1 is greater, then you are taking this x plus r as the minimum, and if x plus r is greater, then you are taking 1 as the minimum. So of course this will be inside U. And remember, this is an interval, it has infinitely many points, so this implies U intersection 0 1, to take this, and this is infinite, in fact it's a uncountable set, and if you remove even a single point from this set, still it will be uncountable set, or infinite set. So this implies this will be non-empty, and hence this x is limit point of 0 1, and this will exhaust your all cases, because your first case you have taken all the points from minus infinity to 0, then the second case you have taken 1 including to infinity, and then in the third case you have taken from close interval, let me write it properly, close interval 0 open interval 1, and that will take the care of all the real numbers. And we notice that the only limit points are the points in between this set, and hence the derived set, therefore the derived set of open interval 0 1 in R with lower limit topology is close interval 0 open interval 1. Okay, I hope the example is very clear. In the next video also we will see one example wherein we will see what is the derived set for same set. We will take same set open interval 0 1, and we will try to find the derived set of this set in R with visual topology, and then you can see what is the difference. Okay, so this topology, the topology in which you are working, is also plays a crucial role in finding the derived set, because we are dealing with the open set, closed set, and that comes from the definition of topology. Okay, so I hope the example is clear, the definition is clear. So stay tuned for the next video.